Hey guys, let's go ahead and continue our discussion on limits at infinity, and we're going to talk about rational functions in particular here. So we'll do a few simple examples here, and then we'll talk about the proper way, so to speak, of how to do this in general with rational functions. And then in the next video, we'll talk about a shortcut that works pretty nicely for rational functions. And it also works for more complicated functions in general, but we'll talk about that all later. So for now, let's go ahead and start with a simple example here. So doing limits at infinity with rational functions, it's pretty straightforward if you have the graph, like we saw in the last video. But let's go ahead and talk about how to think about it algebraically. So we have f of x equals 1 over x. So let's go ahead and think about how to find the limit as x goes to positive infinity of f of x algebraically. So actually, let's go ahead and write 1 over x here. Okay, so we're taking a limit as x goes to positive infinity of 1 over x. So the idea here, when x goes to positive infinity, basically what that means is it's just shooting off really far to the right in the positive direction there. And basically the idea is that x is getting really super huge. So what we have here is 1 divided by super huge numbers, all right? And when you have a fixed number on top, you know, whether it's 1, 2, 3, even if it's something like 10 billion, doesn't matter how big it is, the point is the number on top is fixed, it's a constant, but the number on the bottom, x, keeps growing without bound. It gets larger and larger and larger and it never stops growing. So what we have is a fixed number divided by something that just gets infinitely huge. It just never stops growing. So number divided by something huge, that goes to 0. And you can try it in a calculator. What if x is 10? Then you have 1 over 10. Okay, 0.1. Not really that small, but what if x is 100? Then you have 1 over 100, 0.01, right? What if x is 10 million? Then you have 1 over 10 million, which is a pretty small number, right? So as x gets larger and larger, 1 over x is getting closer and closer to 0. So this limit then is 0. That's as x goes to positive infinity. What about negative infinity? So let's take the limit as x goes to negative infinity of 1 over x. Well, it's pretty much going to be the same idea, just now x is going in the left direction, you know, the negative direction here, and the idea is still the same. X is getting really super huge. These numbers are huge. Huge negative number means far away from 0. So x is really super huge, and what we have is 1 divided by a super huge negative number. So what that means is we're going to get an answer that's negative, but it's a really tiny negative number, which means it's a negative number close to 0. So just like before, now we can imagine what if x is negative 10? Then we have 1 over negative 10, which is negative 0.1. What if we have x equals negative 100? Then 1 over negative 100 is negative 0.01, right? So even closer to 0. And if x is negative 10 million, that's a pretty big negative number, right? So 1 over negative 10 million is going to be a really teeny tiny negative number close to 0. So again, this limit is 0 here. So that's kind of the idea, is what you want to think about in general is when we have something like this, it's just a fixed number divided by something that's just growing really far away from 0. And in this case, it doesn't matter if it goes far to the right or far to the left. So let's just look at the graph for this really quick, just to confirm this here. So x-axis, y-axis, and we know 1 over x, the graph of that just kind of sort of looks like this, roughly. And it's got this horizontal asymptote here at y equals 0, and it's got a vertical asymptote here at x equals 0, but that's, the vertical asymptote's actually irrelevant. But this horizontal asymptote here, we see that as x goes really far off to the right, the y values are approaching the horizontal asymptote, which is y equals 0. And as x goes really far to the left, the y values again are approaching the horizontal asymptote, y equals 0. So that's why these limits are what they are. Okay, so that's example 1. Let's go ahead and move on to example 2. Example 2 is pretty much the same idea. The function's a little more complicated, but it's really not going to be that much worse. So let's do limits as x goes to positive infinity of negative 3 over x squared plus 5. And again, these parentheses, they are necessary because we have this addition in here. So we're taking the limit of this entire thing here. So don't forget to include the parentheses. So what's happening here? X is going really far to the right, okay, because we're taking the limit as x goes to positive infinity. So x shoots off really far to the right, and what happens is x increases without bound, so x squared does the same thing. So as x grows and grows and grows and moves off really far to the right, x squared does the same thing, even faster in fact. So now what we have is negative 3 divided by x squared. So x squared, that's a positive number, right? It's a really, really huge positive number. And negative 3, that's negative 3. So negative 3 divided by a super huge positive number is something negative, really teeny tiny, close to 0. But it's pretty much going to be the same idea as in example 1. As x goes off to positive infinity, x squared just gets really huge and never stops getting huge. It just keeps growing and growing and never stops. And then negative 3 divided by something huge is going to get closer and closer to 0. So this part just goes to 0, and then plus 5, there's no x on here, so whatever happens with x is completely irrelevant for this plus 5 here. So what we're actually left with is 0 plus 5, or in other words, just 5. Okay? So that's limit as x goes to positive infinity. What if we take the limit as x goes to negative infinity? Then the same thing pretty much is going to happen. Now x is going off to negative infinity, and as x shoots off to negative infinity, x squared, where does that go? Well, x squared becomes positive, right? So if you take a negative number squared, you of course get a positive number, right? So as x shoots off to negative infinity, x squared is going to positive infinity even faster. But the point is that x squared is just getting really super huge, far away from 0. So just like before, now we have negative 3 divided by something really super huge. So it's a negative number, really teeny tiny, close to 0. So as x goes to a negative infinity, x squared shoots off to positive infinity, really far from 0. And negative 3 divided by x squared just approaches 0. So again, this is going to be 0 plus 5, or in other words, just 5. Because when you divide a fixed number by a super huge number, you're going to get something really teeny tiny, close to 0. That's the key here for this type of stuff here. That's the important fact to remember here. Fixed number divided by something growing really super huge, close to 0. That's what you want to remember. Let's take a look at the graph here real quick. So negative 3 over x squared plus 5, the graph for that x-axis, let's see, y-axis. So negative 3 over x squared plus 5 is kind of sort of going to look a little something like this. These pieces should actually look more symmetric, but it doesn't really matter, I guess, for this. And this is the line y equals 5 here. So here's our function, both of these pieces here, that's negative 3 over x squared plus 5. And we see that as x goes off to positive infinity, the y coordinates are going off to 5 here. They're approaching this asymptote. And the same thing if x goes in the negative direction. Okay, as x shoots off to negative infinity, the y values are approaching positive 5 still. So that's what's happening there with example 2. So let's go ahead and do one more example that's a little more complicated, but we're going to use this idea here that we've been using in example 1 and 2. And for example 3, we're going to see something that's the proper way to do this stuff, so to speak. And there is a shortcut. It's a really nice shortcut that we'll see in the next video. But for now, let's go ahead and do example 3 here, which is what? Limit as x goes to positive infinity of x squared minus 1 divided by 5x cubed plus 6. Alright. So what's going on here? So it's a little more complicated. It's not just 1 over x, it's not just negative 3 over x squared plus some constant. It's a legit polynomial divided by another one here. So remember, that's what a rational function is in general, right? It's just a polynomial divided by another polynomial. So just a brief refresher on that. A polynomial is something that involves a variable, usually x or y or z or t, whatever you want to call it, a variable x here. And all the powers of x, they have to be positive integers, or they could just be constant numbers, which basically means x to the 0 power. So you can have your variable here, and in a polynomial, the variable can only have positive integer powers or power 0, which means a constant here. So, and the coefficients here, this is a 1x squared, that's a minus 1, that's a 5, that's a 6. So they can be any real numbers you want. But the point is, for a rational function, you've got a polynomial divided by another polynomial. And remember, the degree of a polynomial is the highest power of x that appears. So here, the degree of the top is 2, because x squared is the highest power of x that appears. The degree of the bottom is 3, because 5x cubed, that's the highest power of x that appears in the bottom, right? So we're actually going to use that fact here. The degree of the top is 2, the degree of the bottom is 3. So 3 is the largest degree that appears anywhere here. So what we're going to do then is multiply the top and the bottom by 1 over x cubed. And why are we going to do that? Well, we'll see soon. So multiply the top and the bottom by 1 over x cubed. And then we're going to end up with this equals limit as x goes to positive infinity. So let's go ahead and distribute this through and see what happens. X squared times 1 over x cubed gives us x squared over x cubed, right? And then minus 1 over x cubed. So we have that. And then what happens on the bottom? On the bottom we have 5x cubed over x cubed. And then plus 6 over x cubed. Alright, so now we're going to take this and simplify it a little bit. So let's go ahead and do that. We'll move this up here. So this is going to equal the limit as x goes to positive infinity of, how do we simplify this? X squared over x cubed, that's just 1 over x. Minus 1 over x cubed, can't really simplify that. 5x cubed over x cubed, that's just 5, right? And then what happens over here? Plus 6 over x cubed, can't really simplify that. Okay, so now what we're going to do, the next thing we do is just look at each of these separately. And we can do that because the properties of limits say that. So the properties of limits say that we can divide, here what we have is the limit as x goes to infinity of this top divided by this bottom. So we could take the limit of the top and divide it by the limit of the bottom. And then after that, we can split this up into two different limits here. So let's just do all that in one quick step here. So when we look at each piece by itself, let's see what happens. So we're taking the limit as x goes to infinity. What happens here? Well, we have 1 over x, and we know that when x goes to infinity, 1 over x, that's like 1 divided by huge numbers. So this guy goes to 0. Alright? How about this piece over here, 1 over x cubed? Well, it's the exact same idea, actually. So as x goes to positive infinity, x cubed also goes to positive infinity, even quicker, in fact. So this guy also goes to 0. Alright? Now, how about 5? 5, there's no x's here, so 5 just goes to 5. 5 just stays as it is. And then how about 6 over x cubed? Well, it's just like 1 over x cubed. Now, instead of a 1, we have a 6, but that doesn't matter at all. It's still just a fixed number divided by something growing really huge. So as x gets really super huge, this whole thing here just gets closer and closer to 0. So then what we actually have here is, once we take the limit, what we have is 0 minus 0 divided by 5 plus 0, which is actually just 0, right? So that's what's happening here. So this is sort of the official proper way to do this kind of stuff with rational functions. You find out the degree of the top and the degree of the bottom and see which one's bigger. And whichever degree is bigger, you multiply the top and the bottom by 1 over x to that degree. Okay? So here the largest degree that it appears was 3, or the largest power of x that appears is 3. So we multiply the top and the bottom by 1 over x to the third power, and then go through this whole process here. And there is a nice shortcut which we'll talk about in the next video.